I'm going to present system bus model for quantum chemistry. So let me first explain what this is all about. So basically, in quantum chemistry, people are solving molecules and are interested in molecular spectra. And it's a very hard problem, everyone knows. And what we do, we just map it to the system bus model. So system in our case is two orbitals, two electron subsystem of the molecule, and everything else from the environment, which is modeled by a set of oscillators, which are coupled with different strengths to this system. So why we do that? First of all, we just want to translate quantum chemistry Hamiltonians to the form which we understand better, because many of us, me and Mikhail and others, we are condensed matter physicists, and system bus model is used all the time there. So we know how to solve it. And second, of course, we have quantum computing in mind, because the system bus model is more convenient for quantum computer, for programming, because quantum chemistry Hamiltonians, they are expressed in terms of fermionic creation operators, which are very hard to program on quantum computers. People use, for example, this Jordan-Wigner transformation, which leads to very lengthy products of Pauli operators, while our model at the moment has only 3 operators long products. And it can be reduced to 2 if one, let's say, simplifies a bit further. Now, what we do? Basically, first we take a molecule, run Hartree-Fock simulation, and out of it we get Hartree-Fock orbitals and energies. And these energies are depicted here by horizontal lines. Then we identify highest occupied molecular orbital and lowest unoccupied molecular orbital. And this is our system, together with 2 electrons. What is then the bus or environment? These are all possible transitions from W-occupied orbitals to empty, shown by arrows here, including transitions from HOMO-LUMO and 2 empty orbitals, so from W-occupied to LUMO. For singlet molecules, for triplet, even more transitions are possible. Every such transition is an oscillator. And this is all, of course, stems from random phase approximations, RPA. This is done there all the time. Now, as I said, we run Hartree-Fock simulation. We get orbitals, energies, but also we get hopping amplitudes, single particle integrals, and Coulomb repulsion integrals. These are very big arrays sometimes. For example, for typical molecule, one should keep 100, 300 orbitals, small size molecule, I mean. And then the number of these Coulomb integrals is huge, up to 100,000, I don't know. And these are our input parameters for the remaining part of the talk, let's say. Now, this is our system, 2 orbitals and 2 electrons. The system has 6 possible states. If you now write the Hamiltonian, it is 6 by 6 matrix, including all Coulomb interaction terms. And in this matrix, only 4 by 4 block is non-trivial. Why is that? Because of spin conservation, because the eigenstates of this model form a triplet and 3 singlets. Triplet, it is 3 wave functions with same energy, so we don't need to spend qubit on it. So if it would be 6 by 6 matrix, you would need 3 qubits to encode it. But since only this 4 by 4 subblock is important, we can use 2 qubits only. And of course, here there is parameters. These are epsilon is Hartree-Fock energies of the orbitals. P is hopping amplitudes corrected by Hartree-Fock corrections. And U is charging energy of every orbital, and let's say, exchange integral. Everything is defined in terms of Coulomb integrals, which we know from the Hartree-Fock simulation. Now, this is already environment. Suppose we have single transition from W-occupied orbital alpha to M. In principle, it is the same type of system as I just shown before. 2 orbitals, 2 electrons. Hamiltonian looks similar if we cut out everything else. Now we can ignore hopping matrix elements, so zeros everywhere, because of the Hartree-Fock simulation. Hartree-Fock simulation makes Fock matrix diagonal, and these hopping terms, these are elements of the Fock matrix. They should be 0. So we have a rather simple model with 3 2 by 2 subblocks which can be diagonalized. Out of that, we can find eigenstate, ground state, first excited state, second excited state, And basically we keep lowest singlet and first excited singlet and ignore everything else. So we reduce this for two-level system. That is an approximation, of course. But that allows us to use only one qubit for every transition, or one oscillator, depending on what we want to, let's say, approximate. Now, these transitions, they are not independent. They interact with each other. And the interaction terms is here. It is basically proportional. Interaction is proportional to Coulomb integral, which connects these two transitions. I can show that, so basically a bit complicated, but it is like this. At the end, we have Hamiltonian of the bus or environment in this form. It is a set of interacting oscillators. Of course, in condensed matter, people like oscillators in the environment which do not interact. This, of course, can be done by diagonalizing this Hamiltonian and introducing normal modes, and then we arrive at this simple Hamiltonian, which is RPA Hamiltonian of a molecule, without our system homolum orbitals. Now, what remains is a coupling between the bus and the. So this is our system, two orbitals, two electrons. One can either change the level splitting or change the hopping matrix element between them. There are two types of coupling between system and the environment. G12 is hopping, and G11 and G22 is level splitting. They both fluctuate because of the coupling to the environment. And the coupling term looks like this. Or this is oscillator operators B and B dagger, or one can replace them by qubits, such that B plus B dagger equals to sigma x. This is actually always possible because excitations are very weak for most molecules which I have checked. One can choose oscillator bus, qubit bus, doesn't matter. Numerically it's the same. So basically this is summary of the full Hamiltonian. We have three terms: system, environment, and interaction. System requires 2 qubits, environment requires many qubits, depending how many transitions you want to keep. Interaction includes these products of 3 qubit operators, sigma x from the environment and some operators from the system. And V0, it is some correction term, which is not so important, I skip for the moment, but it is there. Now, this man might think, okay, I got this Hamiltonian, what's the benefit? Because original Hamiltonian of a molecule was very hard to solve. This one is maybe even harder. In fact, it is not. It is easier to solve because coupling constants G are very small for all molecules. Or not all, of course, but for most. Then one can just make perturbation series in G. In this case, it is like deriving Lindblad equation. But since Lindblad equation in this case has an environment with very big gap, there's no damping term, no dissipation. The only thing which one gets is lump shift, which is given by this integral. And this lump shift can be solved for by, let's say, Markovian approximation, which is usually done. At the end, what one gets, just system Hamiltonian of the same form with the normalized parameters. And these are just corrections proportional to coupling constant squared divided by omega. This is very easy to solve. And actually works quite well for many molecules. And this is an example. This one molecule, cyclopentadiene. Looks like this. And then these are coupling constants versus frequency of the oscillators. Many modes are involved. So to solve such an object, one should keep basically all transitions, but out of them, let's say only few are important ones. What is shown in this plot, I sort these peaks and take the strongest first, and the rest I solve approximately in the same way as I've shown before, but a static screen approximation or lump shift. And then I vary the number of qubits, which I solve exactly. And I get in, and what is plotted here is the first excitation energy, triplet state, first excited triplet minus ground state singlet. And these points are shown what I'm solving my model, what I'm getting. And this orange line is static approximation when, let's say, all qubits are put into lamp shift. And this dotted line is a very accurate calculation, which my colleague Reza has done. I don't know this method, MRAQCC. So CC is coupled cluster, the rest I don't know. But what is important is that the total number of transitions is 4,000, and the chemical accuracy is achieved for this molecule. Chemical accuracy is 1 kilocalorie per mole, which is 0.043 electron volt. If you see here, it is achieved for this molecule. Next, these are 3 other molecules. So basically, one is the same, and 2 others, for which we also achieve this chemical accuracy. And error is quite small for all of them. I do the same thing. Actually, by now, we have identified already 6 molecules, which are good. Now, this table is just to show that this static approximation is working quite well. So what I did here, I basically benchmarked. There is a nice database, which is called Quest, where they summarize, I would say, 60 or more molecules, for which very accurate quantum simulations have been made. And vertical excitation energy for all of them are provided so that one can easily benchmark various methods against that. That's what I did here. So basically, the static approximation gives the error 0.3 electron volt. I selected 20 molecules which are good. These molecules are actually weakly correlated, so DFT is also working nicely for them. And DFT gives the same accuracy for the lowest singlet excitation and a bit better for low triplets. That's what I'm getting. But anyway, it just demonstrates that this approximation which we are developing is quite accurate. For, let's say, for general molecule, you get 0.3 electron volt error, but for some, you can achieve quantum accuracy, which is very good. So there is another illustration, let's say, certain d-radical molecules, which are hard to solve. They are strongly correlated. And in this case, DFT is not working well. But this model which I'm presenting is working quite well. So the error is average error over certain molecules at 0.2 electron volt, which is still not chemical accuracy, but not far. Well, so basically it's my summary. We developed this system bus model for quantum chemistry, and it provides chemical accuracy for some molecules, not for all, of course, because it's approximate. And also, let's say, can be convenient for quantum computing. And this static approximation is a cheap computation. So basically, one needs to invert n squared by n squared matrix, where n is the number of orbitals in the chosen basis set. So at this point, I finish. Thank you for your attention.